Okay, all right, let's get started. It's our pleasure to have Sam Coday here today from Berkeley. Her works on power electronics for all kinds of applications. And Sam, take it away.
Awesome. Okay, thank you so much for having me. I'm excited to be here today and to share a little bit about some of my research, which focuses on power electronics and the role it can play in future electrification and a more renewable future. I'll start off today by talking about high-performance power electronics, kind of focusing in on what does high performance mean, what are we looking for when we design these converters, and then I'll move on to a subclass of converters called hybrid switched capacitor converters. And I'll motivate why this class of converters is uniquely well-suited to handle the challenges that lay ahead. And then I'll talk about two specific examples. One is a hybrid switched capacitor converter designed for hybrid electric aircraft, and the next is one designed for future space travel. And then finally, I'll finish today by talking about next generation converters. Really, what are we looking for as we move into this next era of power electronics suited for a more renewable future? So let's start off first by talking about high performance power electronics. Now, if you're unfamiliar with this field, simply put, it is the study of how to convert one type of electrical power into another type of electrical power. And we want to do this in the most efficient and reliable and all of these different things. And power electronics is all around us. So inside your phone, there's low voltage power electronics, and there's power converters to charge our laptops, and all the way up to grid scale utility. So I could pick any number of examples to start with, but I'm going to start with one that's a little close to home. Similar to here, I live in Berkeley, where we have frequent power safety shutoffs due to wildfires and other intermittent fault issues. So grid scale battery storage is one such solution for this problem. Here on the right-hand side, I am showing grid scale battery installation growth over the past few years. And what I want you to take note of is that there's been a lot of grid scale battery installation growth, particularly in the United States and elsewhere. If we focus in on what power electronics we need to have grid scale battery storage, we need an inverter, which takes DC and turns it into AC, such that we can discharge the batteries onto the grid, offering support, which is the job of the grid scale battery storage. We also need this power electronics to be bidirectional, meaning at certain parts of the day, you're going to charge up these batteries, and at other parts, you're going to discharge. Furthermore, we want it to be efficient. The more losses you have in the system is just lost power that could be used to support the grid or charge the batteries. Another example is solar generation. Here on the right-hand side, I'm showing solar generation by year. And you'll note the bar on the far right-hand side is the necessary growth we need to hit for net zero emissions by 2050. So we're still really far away from that mark, even though we've had great growth due to mostly the decreasing cost of solar panels. Power electronics also plays a role in this. So here I'm showing one technology, which is a microinverter. I think this is a particularly exciting technology. It sits on the back of each individual solar panel and takes that solar panel and connects it directly to the grid. It increases the modularity and efficiency and can drive down the cost as well. Inside that converter, we have a boost converter, which steps up the voltage, and then an inverter that takes it and connects it to the grid. And so when we're talking about these types of power electronics that we need, we want them to be high performance. And what I mean by that is efficient, reliable, lightweight, small, and low cost. Now, in an ideal world, every single converter we design would be perfectly balanced of all of these things. But in practice, there are trade-offs like anything in engineering. And so we have to look at specific examples to determine what is the most important requirement. So if we look at that example of microinverter that I just mentioned, we really want that converter to be small, right? Because it's going to fit on the back of a solar panel, so it needs to have a very small footprint area. And we really want it to be low cost, right? Because we want to increase the accessibility of solar and make it easier for people to install solar. Now, that's not to say we don't care that the converter is also efficient, reliable, and lightweight. It just means we're going to have to prioritize other things. If we shift our focus to aerospace, which is what we'll primarily talk about today, and let's take the example of hybrid electric aircraft. Here, we want to focus on different metrics: efficient, reliable, and lightweight converters. Reliability, because these converters are sitting right next to a human in an aircraft, so we need them to be reliable. And lightweight and efficient, because if your converter is extremely lossy or heavy, you're going to need more batteries on your aircraft, thus making it even less practical in the future. And so today, we're going to focus on these three main metrics. How do we design efficient, reliable, and lightweight converters such that we can enable future electric aircraft and space travel? Which leads us to hybrid switched capacitor converters. These are a class of converters that are well suited for reliable, efficient, and lightweight conversion. Let's take a step back and look at power electronics. As I mentioned, it's taking one type of electrical power and turning it into another type of electrical power. So let's say we're given this problem. We have some high DC voltage, and we want to turn it into a lower DC voltage. And we would take a look at our toolbox. How can we do this? How can we orient our different devices to do this? And we have passive components. This is going to be our inductor and our capacitors. And this allows us to store and process energy. And then we have active components. These are our switches. And our job as a power electronics engineer is to see how we can orient all of these different devices to create the best power electronics converter. So if we take a closer look at our passive components, the inductor and the capacitor, here I'm showing all of the commercially available capacitors and inductors on DigiKey. And I'm plotting their energy density. So for a capacitor, that's going to be 1/2 CV squared divided by its volume. For an inductor, 1/2 Li squared divided by its volume. And what we find is that the best possible capacitor has over 1,000 times higher energy density than the best possible inductor. Another way of looking at that is here I have 2 capacitors placed on top of an inductor, and that inductor can store 4 millijoules. Those 2 capacitors can store 80 millijoules. So we can store 20 times more energy in a 22 times smaller volume. And so simply put, if we can use capacitors as our primary energy storage element, we can create more dense and lightweight converters. Now, how we actually do this, we now need to look at topologies. So typically, if I were to give you that problem of turning a high DC voltage into a lower DC voltage, you would use a buck converter. This is maybe what you would learn in an Intro to Power Electronics course. And this is a switched inductor converter. You might see why. We have some switches and an inductor. Now, in this topology, the inductor is doing all of the work. However, we can add a capacitor to this network. This is called a flying capacitor because it's not referenced to a ground node. And we're shifting some of the work onto the capacitor and away from the inductor. This means we can effectively decrease the size requirements on our inductor. And in fact, we can keep doing this and keep adding capacitors and more switches and create a higher order network of capacitors and really shrink that size of the inductor. And this is what we call a capacitor-based converter, and specifically a hybrid switched capacitor converter. So it's built up of a switch network with flying capacitors. That's why it's called switched capacitor. And then it's called hybrid because we are still going to leave a little bit of inductance in this network. Sometimes people want to get rid of that inductor, but by keeping it in, we're able to regulate and softly charge our capacitors. We won't get into that too much today, but it adds some benefits. But we really don't like it. It's really big and bulky, so we want to shrink it as much as possible. And so that's the work of hybrid switched capacitor converters. Just utilize the fact that capacitors have much higher energy density. Yes?
But you also need the more switches, right?
Yes, and we will talk about that a lot today, all of these switches. And so this is one of the primary concerns of these topologies. There's a lot of switches and a lot of capacitors. And in fact, my first conference I went to, there was a professor, and they said, no way is this ever going to fly. And so today we're going to answer that question, and I'll show you a flight-qualified version of a much higher order network even than this. And so when we look at these topologies, that was just one example of a hybrid switch capacitor converter. There are many, many more, even more than are listed here. And we're not going to go into the specifics of how we turn on these switches or operate. But what I want you to see is, in general, we have a lot of capacitors, a lot of switches, and usually just one inductor or some very small amount of inductance that we're going to use in this family of hybrid switch capacitor converters. And now I think the question I just had leads really well into this next point, which is hybrid switch capacitor converters are being used at lower voltages right now. So particularly in data centers, there are people interested in some lower order networks of these topologies, 48 volts to point of load. Now, some of the most exciting applications, in my opinion, moving forward, these solar or hybrid electric aircraft, we need higher voltages. And so we need to tackle some even more large challenges in order to take these topologies and use them in the real world. One of the main things is higher switching losses. Anytime you take one of those switches and you turn it on or turn it off, you have some amount of loss associated with that action. It is proportional to your blocking voltage, so as we move to higher voltage, we're going to have higher switching losses. Again, if we look at higher voltage, typically if you take a design and you move it to higher voltage, you spread it out. That's kind of the intuition to deal with clearances. That adds a lot of really awful parasitics in our converter, so we have to look at careful design practices, control techniques that allow us to safely start up, shut down, and deal with transients, and then component characterization. I said we want to use these capacitors, but there's actually a lot of questions about how to use these capacitors in the most effective way possible. And so this is some of the challenges that we'll talk about today. And we'll start with an example of a converter designed for hybrid electric aircraft applications. and kind of walk through some of the design process. We care about electric aircraft because by 2050, the number of aircraft passengers is expected to triple. This is at the same time that we as a global community are working to reduce our emissions. And hybrid electric and eventually fully electric aircraft offer solutions to reduce fuel consumption, maintenance, and noise. Here I'm showing 2 examples of some ideas in all-electric and hybrid electric aircraft. However, to get ideas like these and more off the ground, we need innovation within the electric drivetrain. So a typical electric drivetrain, you're going to have a battery or a series of batteries, a DC bus, an inverter, and an electric motor. This is also similar in an electric vehicle. And here, what we care about is the specific power. This is measured in terms of kilowatt per kilogram. So how much power we can process per weight. We want this number to be as big as possible. And we also want it to be efficient, so less losses, not only because that's just burned power, but also because it's going to heat up our system if we have losses. So we really want to decrease those losses as much as possible. If we look at this conventional architecture for hybrid electric aircraft or fully electric aircraft, there are a number of challenges that exist. The biggest one being that the DC bus voltage is dictated by battery voltage, right? If you have them directly connected, as the battery voltage changes through state of charge, your DC bus voltage will change. That means that we might have a lower DC bus voltage, depending on our different operating conditions. Lower voltage for the same amount of power means higher conduction losses. And that means we need heavier transmission lines. This is actually one of the heaviest components in these architectures, and we really want to minimize this. Let's say we did want to increase the voltage on our DC bus, we would need to have higher voltage batteries or series stack batteries. This is difficult to do at altitude where voltage clearance is a really big concern. And then finally, it means our inverter is going to need to operate at a wide range of DC input voltages, making it less efficient than if it had one fixed conversion ratio. So what we're doing in this work is adding an additional stage. This is a regulation stage between the battery and the DC bus. This means the DC bus can stay constant irregardless of battery state of charge, and we can make it as high voltage as we want. In this work, we're going to talk about a 750 volt DC bus, but there's many people who are suggesting for future electric aircraft, we could go as high as 2 kilovolt or even 3 kilovolt DC bus. It also means our batteries can remain low voltage and safer and easier to produce while maintaining this high voltage DC bus. And lastly, our inverter can have one fixed input voltage, meaning it can just be more efficient across a range of load conditions. Now, this is an additional stage, and I said that we want the full system to be as lightweight and as efficient as possible. So it is absolutely important that this additional stage be extremely lightweight and efficient. And so that's what we'll talk about in this section, is how to design this lightweight and efficient converter. Now, if you remember that spider chart I showed earlier, we also care about reliability. And in fact, this work was actually to answer the question that we just got. Those are a lot of switches and a lot of capacitors. Is this really reliable? And so we took this converter and in collaboration with Ampere, a hybrid electric aircraft company, and with some funding from RPE, and fully flight qualified the converter for low altitude aircraft. A little bit about this company that we're working with, Ampere. They take old Cessnas and they gut them and they make them hybrid electric. It's a pretty cool business model in my opinion. And they're already doing some short flights, so particularly Hawaii, where you want to jump between islands. And they're seeing some really great reductions in fuel, as well as maintenance, noise, cost. So it's really exciting to work with them. And we're going to talk about the flight qualification here in a few minutes, but let's first focus on this question of how to design a lightweight and efficient converter. So here we're going to look at a hybrid switch capacitor converter, like I mentioned earlier, and it's called the flying capacitor multi-level converter. It's what's shown on the right-hand side. And hopefully this looks familiar. We have a lot of capacitors, a lot of switches, and one inductor. Now it's helpful when talking about the FCML to compare it to a conventional boost converter, which is a switched inductor converter. This is how you would typically do it, just so we can understand maybe the trade-offs or the benefits. First, even though we have more switches, each switch is only going to see a fraction of the output voltage. So we can have a high output voltage, and the switches can actually be rated for lower voltage. And this is a function of your level count. So the FCML structure is these complementary switch pairs and flying capacitors, and they're like Lego blocks. You can keep building them up and to achieve a higher level count converter. Higher level count means lower voltage stress on your switches. In general, if we look at the figures of merit, we want to use lower voltage switches in our designs because they're going to have less losses even if we have more of them. And then if we take a look at our inductor, the inductor frequency is increased by an order of n-1, and the ripple amplitude is decreased by an order of n-1. This means you're effectively decreasing your volt-second requirement on your inductor by an order of n-1 squared. So we're really able to shrink the size of our inductor, which is kind of the whole point of moving to hybrid switch capacitor converters. So this is the flying capacitor multi-level converter. And the most important question when designing this converter is how many levels is enough? Should we choose a 2-level count, or should we go up to 2,000? And this is actually a pretty complicated question to answer. If we look at lower level counts, the weight of our converter is going to be dominated by our inductor and our switches. So we're not going to get really that benefit of moving towards a higher level count where you can decrease the requirement on your inductor. However, if we move to a really, really high level count, we're going to have hundreds of capacitors and hundreds of switches. These components in general are more lightweight than the inductors and the large voltage switches, but having a lot of them is going to contribute significantly to the weight of our converter. And so you can start to see the optimization maybe you could write of, okay, how to minimize the weight of this converter. But unfortunately, we don't even have all the information we need to solve this problem. If you were to go to DigiKey and you were to say, I want the most lightweight capacitor possible, you would have a hard time, because typically all we're given is the volume of these components, not the mass. And so one of the students I work with, Jure, worked to painstakingly weigh hundreds of capacitors so that he could develop a model that tells us the density of a specific component based off of its rated characteristics. And so based off of this, we now have the information we need in order to model the capacitor weight and the inductor weight in our design. But that's not the end of the question. We also said we wanted to design a lightweight converter. And so here, again, we need to balance losses associated with our switches, so conduction losses as well as switching losses. Inductor losses, and I will say this is an entire field of research. There are people in power electronics that dedicate their life's work to decreasing inductor losses and finding new ways to operate inductors. And so this is a very complex problem. We also have gate drive losses. So almost all of the switches in these converters are not ground referenced, meaning you need to switch them using some complicated gate drive network. And then finally, we have capacitor losses. These losses are usually neglected because they're significantly smaller than inductor losses. But now we're going to be talking about converters that have hundreds of capacitors. So even if their losses are small, they start to really add up. And this is actually what my master's thesis work focused on, was investigating the loss metrics for these multi-layer ceramic capacitors. This is a specific type of capacitor we use a lot in power electronics. Really high energy density because it's built up of these interwoven plates. So really increasing the capacitance per unit volume or mass. And so here we're interested in the loss of these capacitors, and we model that with an equivalent series resistance to help us understand the real part of the loss. And if you were to go and look at the data sheet of these capacitors, you would find a plot like the one on the right-hand side, which shows the equivalent series resistance as a function of switching frequency. However, this is measured at 0 volts DC bias and 0.1 volts RMS sinusoidal excitation. Unfortunately, that is not at all how we're using these devices. If we take a look inside the flying capacitor multi-level converter, these capacitors experience hundreds of volts of DC bias, large signal excitation, and it's not sinusoidal, meaning we have effects of higher order harmonics on our losses. And so we built an experimental setup that allows us to have a device under test where we can vary the frequency, the AC amplitude, and the DC bias to understand how these characteristics affect the loss of our components. Unfortunately, you can't use electrical measurements here due to the inaccuracy of those measurements. So we use a calometric measurement where you take the device under test, you dip it in an oil bath, and you measure the temperature rise of that oil bath. I will be the first one to admit that this is an extremely tedious thing. So we developed a model so that designers don't have to go buy a temperature chamber and an oil bath and do all these measurements themselves. And instead, they can look at this model, which is very simple, that says the biggest impact on your capacitor losses under these operating conditions is DC bias. So if you take these capacitors, you operate them with a large DC bias, which is how we're typically operating them, your losses actually might be 6 times what they are if you were to use the datasheet value. And it's pretty linear. It's not quite linear, but you can use this model and better inform your losses. Now, what's really exciting is after publishing this work, it's been a number of years, and now manufacturers are actually starting to include models and models like these on their websites because they know that people are wanting to use their capacitors in these unique ways. I'm also showing some work done by ETH Zurich, Professor Kohler's group, which looks at the harmonic decomposition. So lots of work has been done trying to understand how to better model these losses in these capacitors for future capacitor-based converters. Okay, so that answers one question, right? We kind of know what our capacitor losses are, so we're able to start looking at the balance of losses. But this is a very non-linear, non-trivial problem, so we're going to use an optimization scheme where we have fixed parameters such as the input-output voltage and power, and then we have a database of components, so different capacitors, switches, inductors that are available online. And we generate random solutions, so varying the switching frequency, level count, and components within that database. And we calculate their approximate losses using that capacitor loss model I just talked about, and then some other loss models. And then we also approximate the weight of the converter, again, using the work that I mentioned earlier. And we were able to find a 10-level flying capacitor multi-level converter, which nicely minimizes both loss and mass. If you were to compare this to the best possible conventional switched inductor converter, that's what's shown in the red triangle there. So you can see the benefit of moving to a switched capacitor converter. Here is the schematic of the 10-level flying capacitor multi-level converter. Yes?
So was this optimization also looking at topologies, or was the topology fixed?
The topology was fixed. So we want to use a flying capacitor multi-level converter, but we want to know how many level count, things like that. But I love that question because that is something that we're definitely looking forward to in the future is, okay, what if you don't fix the topology? You know, looking at, I mentioned all of those different topologies we could use. What if we vary those as well? And so I'll mention some work at the end that talks about that. So here we're looking at a 750 volts output. It can operate at a wider range, but for flight qualification testing, we have a fixed output voltage and fixed power of 1.6 kilowatts. And we're going to use these GaN devices, which have very low losses, in order to implement the switches. We take a look at the hardware. So this is a printed circuit board designed for this application. Moving from left to right, we have the microcontroller, which generates our gate signals, does the control, all of that good stuff. Then we have an inductor. You can see we were able to decrease the size of our inductor compared to a switched inductor converter. It's still one of the largest components on our board, so you can really see the bottleneck of magnetics. And then we have all of our GaN devices there in the center and our flying capacitors on either side. This is a dual-sided design, meaning if you were to flip over the board, you would see the same thing on the other side. If we look at a brief overview of the performance of this converter, we have a peak efficiency of 99.52% and a specific power density of 28.3 kilowatts per kilogram. Now, just for a point of reference, if you were to go and try and buy a converter off the shelf with similar specs, this is about a 6 times improvement in the specific power density. So this is really exciting, but now the next question becomes, how do we actually take this converter and solve some of the implementation challenges that allow us to move on to flight qualification testing? One of the biggest challenges with these converter topologies, or any capacitor-based topology, is you need to pre-charge your circuit some way. If you just slam on the input voltage, those capacitors can't instantaneously change voltage, and therefore you're going to have a cascading failure, which is not good. And so here we investigated some different techniques for startup in order to safely start up at high voltages. And so you can see one technique here. We have a constant current-enabled MOSFET that drives up the capacitor voltages in a nice ramp and safely does so. Another impact of this work was looking at shutdown. So similar to startup, if you were to just disconnect all of your switches and enter shutdown mode, you have a lot of different capacitors charged different voltages with different RC time constants. And as a result, you're going to, again, have a series of cascading failures. This is a one-time use converter, and that's not what we want. So here, we investigated some different techniques to safely shut down your converter. And we produced this model that allows designers to put in, okay, what's my level count, output voltage, component characteristics, and how can I safely shut down? So there are a few different techniques you can use. Ultimately, the idea is to incorporate this stage of optimization in the initial design stage. So as you're picking converter topologies, you know whether or not you would have safe shutdown. We built all of this into one larger system. So here, the blue board shown is the flying capacitor multi-level converter we talked about. And then we have some other boards that allow us to connect to the aircraft itself. We have input relays and output relays for safety, startup, and shutdown. A logic power board that takes the 28 volts on the aircraft and turns it into bus voltages for our sensing and control. And then we have a telemetry board which senses and stores data. Now, for initial flight qualification testing, and this is typically how it's done, you want to be non-mission critical. So meaning we are going to connect to the battery on the input side, but we're not going to connect to the motor just yet on the output side. We have to do initial flight qualification testing such that if we fail, we aren't going to take down the aircraft. And so that's why we carry our own load. So that large portion at the bottom is actually 50-pound load, which we also had to flight qualify, which was harder to flight qualify than the rest of it. And so let me talk very briefly about flight qualification, just some of the testing that we did. First, we have vibration testing. So here is an acceleration table. We were able to collaborate here with Lawrence Berkeley National Lab, their space sciences group, to use their acceleration setup. And so we have lots of different sensors placed around our system that tells us the acceleration our system is seeing. And here, see if the video works, yeah. So here I am showing testing in the z-axis. That table actually tilts so you can test in the x and y-axis as well. And for each test, we sweep the frequency of the acceleration. This video is actually taken at very low frequencies, because once it gets up to higher frequencies, you can't actually see it shaking with your eyes. And so for each test, we followed the sweep shown on the bottom left-hand side. Each test lasted an hour at full voltage. And so we did 3 hours of full voltage vibration testing, really looking to see, are these converters capable of withstanding this kind of system pressure. We also did shock testing. This is a mechanical test to show that we can handle sustained 9G for 3 seconds, also in the X, Y, and Z axis. That one, you can like barely see it shake. You can just see the wire shake. We also did thermal testing. This is low altitude aircraft, so we only had to show that we could handle 2 hours at a 55-degree temperature. So we used a thermal chamber, and over 2 hours made sure we didn't have any thermal runaway. Everything was within nominal operating conditions, and so that's what we see here. Now, we've passed flight qualification testing for low altitude aircraft, and we are currently in the process of Ironbird testing, meaning we're taking our system and actually installing it on one of Ampere's aircrafts. So you can see it says experimental really big on the side there. And their batteries, I don't know if the pointer works, but the batteries are down below. And then our system is mounted on this shelf here. And we are actually hoping to fly our full system in the next coming months, which is quite exciting. We're going to shift our focus now away from aircraft and onto spacecraft and kind of give a different flavor of hybrid switch capacitor converters. Now, I grew up outside of Houston, so I think space is cool. But in case you don't, here is a very cool infographic showing some of the technology advancement that we need as we look towards putting humans on Mars. And there's a lot of things we need to do. We need advanced robotic systems, and that's what we'll talk about today. We need to be able to further explore the habitat that we're looking at. There's discussion of a lunar base and how to actually power that lunar base. Small satellites and large aircrafts, both the propulsion of these systems, as well as on board, the solar, anything like that. And right now, we don't have the power electronics to do these things. Particularly because of radiation effects, designing power electronics at high voltage is particularly challenging. And so there's a lot of areas for advancement here. We're going to talk about one example, which is future robotic exploration of space. So here I'm showing 2 rover systems that are designed to better take a look at the lunar and Martian landscape. And both of them require a high voltage DC tether to transmit their power. So the architecture looks something like this. You're going to have a power source, a step-up converter, high voltage DC tether, step-down converter, and the rover. Now, similar in the aircraft, we want this tether to have as high a voltage as possible, because the higher the voltage, the lower the conduction losses, the lower that mass of the tether needs to be. And so here we're looking at a 750-volt tether and a 50-volt rover. And we'll focus on the step-down converter. Now, in power electronics, you can typically design for the step-down converter and use the same one for the step-up converter. So we'll just focus on the step-down converter today. And one of the biggest challenges is understanding how to handle the radiation effects of space. So particularly at higher voltage, total ionizing dose and single event effects can really hurt your active devices. So we need to design for that. And then this is a nominal 15-to-1 conversion ratio. Just for reference, that FCML for aircraft we just talked about was maybe 3-to-1 maximum. So this is an extreme conversion ratio. We need to be able to regulate, because similar to power systems, we might have droop on that tether, and we need to be able to regulate at the output for our rover. And then most importantly, it needs to be lightweight and compact. In fact, every kilogram you put into space costs about $2,000, so it really needs to be lightweight. And so there are a number of ways we can tackle these challenges. GaN devices recently have gained a lot of popularity and commercialization. They can handle radiation effects better than their silicon counterparts, so we can use them, but we can only use them at a fraction of their rated voltage. So we're going to need some kind of structure that decreases the voltage rating on our switches. And then we need to be able to handle this extreme conversion ratio. To do this, we're going to use a technique called partial power processing. This isn't a new technique. The idea is if you have a high conversion ratio where you need regulation, let's split it into two sub-problems. We're going to design one converter that is going to have a fixed conversion ratio that's really high, and it's going to process the majority of the power. It's going to be really efficient because you can think of it this way. If you only have one job to do, you're going to be able to do it really well. Same thing with converters. And then the other converter is going to be a regulating style converter, meaning it's going to offer regulation, and it's going to process the minimum amount of power possible. Now, typically, a partial power processing structure is done with what's called a sigma converter. We don't need to get too much into depth with it. It unfortunately won't work for our application because it has high voltage stress on the switches, which isn't going to do well with radiation, and it has magnetic isolation, which is really big and bulky. So we wanted to take a look at this and say, is there a way to do this with capacitive-based converters? And there is. We can use what's called a Dixon-style converter. So here, this is a resonant converter, meaning that you have a tank of capacitors and inductors that you're going to resonate with. And you can use these capacitors, these flying capacitors, to achieve isolation. So similar to how you would use a transformer, we're now going to have capacitive-based isolation. And this kind of goes with theme of capacitor-based converters throughout today's talk. This converter topology is also nice because each switch only has a fraction of the high side voltage, meaning we can use lower voltage switches, which helps with radiation effects. So now the question is how to design this such that it is lightweight and compact. My colleagues and I have recently presented some work looking at how to minimize the volume of your capacitor and your inductor in resonant-style hybrid switch capacitor converters. So pretty much just looking at the question of how big should my inductor be versus how big should my capacitors be. And this is for a wide range of topologies. Taking this same framework, I have applied this to this Dixon converter, instead looking at mass instead of volume, but optimizing the size of our passives. These are the heaviest components on board. Choosing a capacitor and an inductor that really minimizes the weight of our total system, which is dependent on the isolation voltage we need to handle. Here is the printed circuit board for this hardware. We have our flying capacitors as the major components there in the center, so you can see why we really wanted to shrink the weight of those components. The switches are actually so small, I don't think you can really see them, but kind of shows, again, the passives are really the limiting factor of weight. Here is a figure showing the isolation barrier of these flying capacitors. So here on the first plot on the left-hand side, I'm showing the flying capacitor voltages with 0 volts of isolation barrier. And then we increase the isolation barrier and we showcase that the flying capacitors readjust and we're able to handle the isolation. The peak efficiency of this converter is almost 97%, which is extremely good for a 12-to-1 conversion ratio, that extreme conversion ratio. And then this figure here shows all of the passives in both the Dixon stage and the regulating stage. In the regulating stage here, we use the flying capacitor multi-level converter, not the same one that we talked about before, but a little bit of a different one. And you can see the work of the partial power processing, meaning that Dixon converter is going to have the majority of the power, majority of the weight, and then the regulating converter is teeny tiny in comparison. Now, this is exciting work, not just because it's a great hardware prototype, but also because it kind of showcases capacitor-based converters. It's not just for this 48 volts low voltage application. We can use it for capacitive isolation and these techniques of high voltage extreme conversion ratios. Which leads me into the final part of today's talk, which is next generation converters and what we're looking for. There are 3 main thrusts, I think, that are important when focusing on the future of hybrid switch capacitor converters within these application spaces. First is advanced manufacturing and cooling, then moving to higher frequency converter operation and control, and then lastly, implementation of novel devices. To talk about manufacturing and thermal, let's take a look back at that flying capacitor multi-level converter. If we look at the weight breakdown of the power stage, the single heaviest component is actually the printed circuit board, which I think is a little surprising, but if you were to feel it, you would understand. It's an advanced stack up, many, many layers inside, heavy copper pores. And so one of our ideas was, what if we minimize the weight of this design? And so Nicole Stokowski, who is an undergrad who I worked with, who's now pursuing her PhD at UWECE, took this and looked at what if we use our PCB more effectively. Instead of having these areas that are just kind of blocked out with the components on top, let's embed the components in the PCB themselves, moving towards maybe instead implementing the components inside the PCB. And so she was able to design this mechanically thin prototype with over 3 kilowatts per cubic inch, which is an extremely competitive power density, for solar microinverter applications. So if you remember at the beginning of the talk, we mentioned microinverters that sit on the back of a solar panel. And so that's for this application here. Now, one of the also great benefits of this type of design is your GaN device is now the tallest component on board, meaning you can cool it more easily. So looking at techniques of advanced heat sink manufacturing, liquid cooling, and immersion cooling, this is going to be a lot easier with this type of prototype. If we take a look at high frequency operation, we want to figure out how to best move to higher frequencies. And this comes from just I equals C dV dt. If you keep everything else the same, increase your switching frequency, your capacitance can decrease. Same with your inductor. If you can move to higher switching frequency, you can decrease the size of your passives. And so one of the first-year graduate students I work with, Alyssa, is looking at how to move to higher switching frequencies and optimize that inductor and capacitor in order to do this in the most effective way possible. Now, one of the big limitations of this is switching losses, which I mentioned earlier. If we look at the loss breakdown of the FCML converter that we talked about, the majority of the losses come from switching transitions. So as I mentioned, every time we switch a switch, you have some amount of loss associated with that action. And so you can do some clever techniques to minimize this loss. One is called zero voltage switching, meaning particularly you can operate a little in resonance style and drive down your blocking voltage before your transition, and you get zero voltage switching. This is going to greatly decrease your switching loss. The issue is with the number of switches we have in these topologies, it's very hard to time this correctly. So you need advanced sensing control in order to do this properly. And then lastly, implementation of novel devices. So something I'm really excited about is monolithic bidirectional switches, which are to be developed in GaN right now. These are 4-quadrant switches, meaning they can block both positive and negative voltage. And so here's a schematic of one of these devices, which was published by Professor Kohler's group at ETH Zurich. I spent this past summer in Zurich working with this group, focusing on how to take these 4-quadrant switches and apply them to hybrid switch capacitor converters. So here we're looking at buck-boost converters. One application space is future electric aircraft, where you might have a fuel cell and battery both on board to power your aircraft. And there are times where you want your converter to buck the voltage, meaning step down, and other times where you want it to boost the voltage, meaning step up. Typically, to do this with a hybrid switch capacitor converter, you would have to take a buck converter and a boost converter and stick them together. That means you have very low utilization of your components because half the time you're not using each set of components fully. And so instead, we developed a new topology utilizing these monolithic bidirectional switches that allow us to operate in both buck mode and boost mode using the same stage of operation. This is a little bit more complicated, but it's still a hybrid switch capacitor converter, still a lot of capacitors, a lot of switches, and then we have 2 small inductors. There are a number of different ways you can operate this converter and even achieving inverter operation with both buck and boost mode. But I think this is a good example of showcasing how new devices really pushes forward power electronics. So as these new devices become developed, it opens new doors for converter topologies, but also new questions. Things like how do we drive these switches reliably? How do we design them to decrease parasitics? Things like this. So there's lots of new questions to be answered as well. So hopefully today I motivated why we need power electronics for future electrification, why hybrid switch capacitor converters are well suited to tackle these challenges, 2 specific examples within aerospace applications, and then a conversation about next generation converters. Lastly, I would like to thank NASA JPL, ARPA-E, and Ampere who financially supported this work and collaborated. Thank you so much for your time.
Thanks, Sam. Any questions from the audience? Yes.
So I was wondering if you had looked at the failure mode of these types of converters and whether increasing the number of stages would reduce its reliability.
Yeah, so that's a great question. Let me restate the question. So looking at failure modes of these types of converters and increasing the level count, obviously, maybe not obviously, unless we do something clever, is going to decrease our reliability. So this is one of the major concerns, and so we did a lot of work looking at reliability for this specific example. Part of our flight qualification was necessary. The first example that I showed, this flying capacitor multi-level converter, was in part due to answer this. Okay, we can design it reliably. Now the next question is, okay, let's quantify this. We need to include it in our Pareto front optimization, or whatever optimization we do needs to include reliability in the future. There's also some clever techniques you can do to control and operate your converter. Let's say one of your switches blows up. Unfortunately, they usually blow up short, which is not what we want. But sometimes if it happens and we can sense it fast enough, we can rearrange the way we're switching such that we can just decrease our level count, which is pretty cool. But we need to be able to sense that and respond really fast. So we're looking at techniques like that. Also, we're looking at how to quantify that. So it's a hard question. One of the things in particular is if you look at soft switching techniques, like I mentioned, so zero voltage switching, intuitively, and there's a little bit of data that shows that that makes switches more reliable, but there's still a lot of work we want to do into understanding these characteristics. Is it actually beneficial to switch softly? And maybe that means some of these higher level count converters are more practical in that application. That's definitely something we're looking at in the future as part of our initial stages of design as well.
Josh, yes.
You mentioned that to safely use scanning devices in high radiation environments, you have to run them at lower voltage. Can you say a little more about what the problems are and why that is?
Yeah, so my understanding is that if you take these devices and operate them at higher voltage, they are more susceptible to these radiation effects. Now, all I know is a little bit about what's going on inside them, but that's definitely, and it's like a really exciting field of research, is how to design switches better. And so you're seeing some of the major manufacturers actually come out with these space radiation hardened switches where they are redesigning aspects of the switch to handle it better. The issue is they're really bulky and they have really poor losses. So definitely an area of future investigation.
Matt? Yeah.
You talk about gate drive when you have a large stack of devices that are spanning a lot of voltage from one side to the other.
Yeah, let me see if I have a good figure. Let's jump. Sorry. Yeah, so I think I have a figure here. Sorry. There we go. OK, so there's a couple of different ways you can do it. You can use isolated gate drive strategy. So you can actually have like a signal transformer, which is going to isolate and allow you to drive. Here we're using what's called a cascaded bootstrap design. So you're in a way charge pumping up the ladder of the switches and their potentials. This works well, but it's more points of failure. So if any of these devices fails, if you look at this is a long chain. Let's say one of those LDOs fails, the rest of your system's going down too. So it's really compact. It's really low cost to do this method, but it's not really reliable and robust. So that is something too, actually in collaboration with NASA JPL, we're looking at better techniques to drive these in an efficient way.
Yeah. June?
Could you speak a little bit about maybe impact on maybe cost and commercializability of different topologies, compared to some of the more conventional?
Yeah, so that's a really good question. The question was about, scaling and cost and commercialization of different topologies. So that's a hard thing to answer right now because a lot of these devices are really cutting edge, so they're pretty expensive. The argument people usually make is, oh, at scale, these are going to come down in cost and all of these things. I don't know that I necessarily truly believe that. But with the work we do for NASA JPL, actually the majority of the cost comes from the weight. So we're really working to minimize the weight with them. Similar with electric aircraft, cost is less of a concern. However, as we move towards applications like microinverters, cost is really important. I would say probably the most important thing. And so looking at things like, okay, adding these additional stages, let's say that does save you something in efficiency and size, what is the comparison and trade-off with cost? And I know that there's lots of people looking into that for the future as well.
Any more questions? Speaker? Yeah.
I think there is a figure about the Pareto front between the mass and the power losses. Yeah, so could you provide some intuition about why the shape of the battleground is quite nice? So kind of you cannot like, yeah, so just increase the mass a little bit, but the loss do not have large impact. Yeah.
So you're saying why is this shape?
Yeah. So the shape is very nice. So kind of you can find the best point of the design.
Yeah, so there's actually like a lot of dots really close to here that are hard to see. So it's actually a really hard thing because once you get this answer, there's a lot of ones that are really close to each other. So we picked one. It may have been the best one, it may not have been. And I will also state, this is using loss models that we're developing. They are not perfect at all. And so this is something that people really are investigating, especially inductor losses are really hard to characterize in an accurate way. As far as the actual shape, I don't know that I've put much thought into it. It is really nice that we get this nice solution. We are bounding things, though. And so I'll say that that's really important, right? This is not all the possible solutions. I am bounding my switching frequency based off some intuition I have as this is a reasonable switching frequency. And I'm bounding the level count, saying I don't want to build a 40 level one, just also from a reliability standpoint. So when you bound constraints on an optimization, you're not getting all possible solutions. And so that's also one thing that, maybe that's why we're getting a nice shape. Maybe if I, relax those constraints, you might get more data points in either region.
Other questions? So if not, let's thank the speaker again, and thanks everyone for coming.
Thanks.